this side is moving that way. This is the position of X, and this is the position of Y at time 1. And the yellow line is a marker that's going to cross the fault. Okay? At time 2, which can be tens to hundreds of years, we have motion of the fault. And we've now, this just shows you the original orientation of the marker, and we've now deformed our yellow line. Okay? This is moving this way a little bit, this is moving this way a little bit. Okay? So that's time 2. So the marker, the yellow line, is now strained. This continues in time. The sides keep moving, and so now you have the marker being more deformed. Okay? So this is elastic strain. Okay? It's changing its shape over time. But at some point it can't handle it anymore and it breaks, and this is the earthquake. But what we can measure with GPS geodesy that we've never been able to do before is this time period in here. What is happening here? Okay? And by looking at that, you can see where in the earthquake cycle you are. Are you close to where it's already ruptured? Or, boy, have you gone dangerously far in terms of strain here that you're going to anticipate an earthquake? So time B and C here is what we call the interseismic period. That's when the fault's locked. It can't break, but it's deforming. And then D is what we call the coseismic. And I'm going to show you that because I'm going to show you the GPS velocities for Haiti for both time periods. Here's the model. Very simple model. Each one of these is a block. These are the faults that were divided into various segments. Okay, so we were going to constrain the amount of displacement that's occurring on each one of these faults and whether or not the faults are locked or they're moving. Okay? And then the fault blocks are rigid, so there's no deformation within the fault blocks themselves. They're just rigid, like a book moving on the surface. Okay, so here's the end result. The end result of that is for the Enriquillo fault, the slip was 7.7 millimeters per year with 100% locking on the fault, meaning that the fault was completely stuck. Okay? We know the last earthquake was in 1751. You can do the calculation just like I can. 257 years. This was for 2008, remember when the paper came out. 257 years times 7.7 is 1.9 meters of slip. 1.9 meters of slip, if it's all released in one earthquake, is approximately a 7.2. So that was the statement that was made. That's it. All right. So, all right, then Haiti happened. All right, so what other information do we have immediately afterwards? Satellites were cast for Haiti immediately afterwards. This is a radar satellite that's owned by the Japanese. The United States currently has no non-classified radar satellites at the moment. And so this is called ALOS. It's L-band, which is 15 to 30 centimeters for those who are not there. This is synthetic aperture radar. Basically, you take a picture before the earthquake, a radar image before the earthquake, take a picture after the earthquake, the ground surface is moved. That means the energy sent down from the radar instrument has to travel a different distance after the earthquake than before. Okay, so there's a time difference between when you send the signal from the satellite to the ground surface and it comes back, and you can look at the difference in the returns and determine how the ground is moving. So this is the raw interferogram, as we call it, from the INSAR. This is the same picture over here. This is a modeled version by a group at Caltech, the USGS group, where this just shows you their model of what the deformation is that best fits this, and they get slip on the order of 1 meter to 1.5 meters. Okay? So that's what this was what was done within a few days of the earthquake. I was actually astonished that they got this done within a few days. Also, a few days after the earthquake, Caltech and the USGS modeled the stress changes that had to occur